This is Free Range Digital Design Foundation Modeling, Chapter 11. So two main concepts in this chapter is working with different circuit forms, and very closely related to that is the notion of minimum cost concepts. The big picture is that in digital design we can represent Boolean functions in many different ways, pretty much an infinite number of ways. So there's an issue of, well, let's represent it in the best way. So there's some standard circuit forms out there that we'll go over, and the best way often is the way that I can do most cheaply, which is essentially a minimum cost issue. But circuit forms is kind of the global description of what we're going to do here. Once again, many ways to represent digital circuits. We've been primarily representing them in two ways. Draw a picture on the next screen. This is a topic covered in other books, and it's covered kind of in a not really consistent manner. We're kind of keep it very basic in this book. My approach is to just show you some simple steps to generate most common forms or most common ways to represent a digital circuit. Like I said, you can represent it in a million different ways, but we want pretty much the easiest way, and that's what we'll be going over here. So I've referred to these forms, standard forms. There are 8 standard forms, and I know how to generate these. So out of those million forms out here, I know what to do with 8 of them, and that's good enough. So closely related to this is the notion of minimum cost. There's going to be 8 different forms for a single equation. Depending on what your parameters are, one is going to be cheaper than the other ones, and we'll step through some examples with that. The standard circuit forms are generated from 2 basic forms which we had, which were SOP and POS. Just as an introduction here, we had SOP and POS, so we'll do this is essentially a SOP type form, sum of products. Here's the sum. These are the products. They're being summed together with this AND OR gate. I'll get this right. So you've seen this 100 times, but there's also, so we're going to call that a special form. We'll run into this again, but this is the classic AND OR form, which means starting from left to right, you run into all the AND gates, and then the results of those AND gates are ORed together. So the other form is going to be this POS form. So if you remember, working with POS, we generated product sums, of course, but essentially this is known as an OR AND form. Okay, so the nice thing about these standard circuit forms is you can generate them from, not memorize anything, but generate them from applications of De Morgan's theorem, and that's what we're going to step towards doing. There's a notion of reduced circuit forms also. Most books cover this in depth. The idea is what we've been using is standard sum of products and standard product of sums, which is really clunky. Essentially, you can reduce that and make less terms in those and be functionally equivalent to the standard sum of products representation. This is an antiquated topic in that typically old books would have you use De Morgan's equation and all the theorems to reduce these equations, and then got into Carnot maps, which Carnot maps are really cool. They help you apply one of the particular theorems to help you reduce equations. The idea with that is it worked great until you had more than 4 inputs to your system. After that point, it didn't work very well. So these reduced circuit forms, in my mind, is a low-level design issue. And if you have to reduce something, go check into the internet, type in Boolean reduction programs. You'll find a lot of programs out there. They're going to do better than you. They're going to do faster than you. Certainly, they're not going to make mistakes. You're going to make mistakes in this one. So once again, modern tools do the reduction for you in most cases, and I've opted not to worry about that. Here's an example of a reduced form here. If I were to expand this using standard sum of products, I has 1, 2, 3, 4, 5, 6, 7, 8, 9. There'd be 9 product terms. Each of them had 4 variables in them. It'd be a huge circuit. You wouldn't want to draw it. But if you know how to do reduction, this giant equation representing this thing in standard SOP form could be reduced to this. And this was something you could plug into software and generate it. So typically you could plug in essentially the index associated with that row, and it will kick out an equation like this. So I've just automatically kicked that out for you. That's what we'll be working with in this. Yeah, so if you don't agree with it, go to the internet, grab a reduction program. It should come out exactly like that. But these two are two equivalent representations. One's Boolean equation, one's compact minterm form. Okay, so here we are. I have this equation here, and what I've advertised is that I'm going to generate these forms based on this equation. And so once again, just to start this off, this is in a classic and/or form. From this form, I'm going to generate some other real classic forms. And I don't have this memorized other than the fact that the starting point is to double complement this. Okay, so once I double complement that, I'm going to apply De Morgan's theorem one time with one of those complements and bring the result down. So the AC, there it is. So we've brought down one of those overbars by using De Morgan's theorem, and we've stopped at this point. And so this, I'm just going to write this down. This is a classic NAND form. Let's look at this thing. This is two terms being ANDed together, and it has an overbar over it. That's a NAND. So here's another NAND. Here's another NAND. Okay, but now what I have here is 1, 2, 3 terms here that are being ANDed together. There's the AND gate. I put your little dot in there. The AND gate has a giant overbar over it, which is another NAND. So what I have there is these inner NANDs and this outer NAND. So this is classic. It's known as NAND form. Okay, so in truth, these are probably the most two common forms out there. And we're going to actually generate a couple more forms just because we can. But I kid you not, and/or and NAND are pretty much the forms you'll be working with more than anything else. So anyway, let's work with this again. What I'm going to do is take this overbar over those inner terms down, and it's going to be A plus C. And so I brought this overbar down. Got to bring this overbar down, and I got to bring that overbar down. So there's my equation, and I have the big overbar over it. Looks kind of junky. Let's clean that up. And giant overbar over it. Okay, so this is another classic form, which is going to be. Look at this very carefully. I see some OR gates on the middle, so that's going to be an OR NAND form. Okay, so there's the OR gates in the middle. These terms are being ANDed together with a giant overbar over it, which makes it into a NAND. Okay, so there's another classic form. Can't say I've ever seen it anywhere, but I certainly know how to generate it without too much trouble. Okay, so the next step here is I'm going to take this overbar down, and this is going to be A. Check that, make sure it actually does look good. It actually does look good. And this is another classic form, which happens to be, I see these two terms being ORed together with the overbar, which is a NOR, and then these things are being ORed together right here with no overbar. That's an OR. So these inner terms are NOR, they're being ORed together, so that's my classic NOR-OR form. Once again, I can't say I've ever seen that anywhere, but I know how to do it. And so last step here is I'm going to take this overbar down, and I'm going to skip a step here, AC, and that's my final term here. And what's classic about this one is what I did was I regenerated the starting term. So once again, this is another AND/OR form. Certainly, if you got to this point, you know you've done it right, because that ending equation matches the beginning equation. So those the previous forms were all generated from SOP form, and now we want to generate 4 more forms, and the starting point is a POS. And so let's crank this out. This is an equation that's written for F bar. You can see the F bar there. It's written in terms of it's the SOP. SOP equation for F bar, which is not what I want. What I need to do before I do anything is change this to SOP form. So this is going to be, this is F double bar, so it's going to be F. That's classic POS form. We know that as OR and form, another word for POS. Looks good. So that's my starting point, and what I'm going to do here is just pull the same trick we did last time, which is essentially all I remember about this thing is do a double overbar and start bringing the overbars down. So the first step, and so this is our first classic form here, and this is going to be NOR form. Okay, super classic. You do see it occasionally here. So what I have is two terms being ORed together with an overbar. That makes it a NOR. Same here, a bunch of terms being ORed together, overbar, another one here. But in the end, I have 1, 2, 3 terms being ORed together with a giant overbar. That's your outside NOR. So this is a classic NOR form. Okay, next step is to bring this overbar down, and I'm going to do this. Okay, that looks right. And so I'm looking at this thing and I see an AND there that's being ORed together with a giant NOR over it. So this is going to be AND NOR form. And I can't say I've ever seen that in real life, but once again, certainly know how to generate it, for what that's worth. Okay, so the last step here, not the last step, but I'm going to take this overbar and bring that down, then this is going to come out. So this is going to be NAND AND form. Okay, so here are the NANDs, individual NANDs, and they're being ANDed together. What makes them a NAND is the fact there's an overbar over it. And so there's my other classic form. So you've seen all 8 forms. What happens here if I do this one more time, I get A plus C bar. And looking good. Okay, looking familiar, of course, because that's really my starting point, which gets me back to that same OR AND form. Okay, so once again, these were 8 standard forms. 2 of them are really popular: OR AND OR, NAND NAND, NOR. They're all generated from, they're generated from SOP equations and POS equations. And all I'm doing is double overbarring these and grinding through with De Morgan's theorem. It works. I don't have to memorize anything other than the fact I have to put an overbar over from the starting point. Minimum cost means that there's a whole bunch of different ways to implement a circuit. And so what's the minimum cost? Okay, so if someone asks you that, the first question you say, or the way you answer it is, you need to define minimum. And so here's a couple issues of minimum here. It could be that your minimum circuit could be based on the number of gates in there, number of devices like integrated circuits. Remember, these circuits, these integrated circuits generally have multiple gates on them. So IC count is practically as important as the gate count, depending on what you're interested in. Oftentimes it's the number of inputs to the gates. I mean, an AND gate can have 2 inputs, and it can have 20 inputs. Certainly 20 inputs is going to be more expensive than 2 inputs. Often, your company may have a bajillion NOR gates on hand, so they're going to want you to implement all your circuits with NOR gates because that's going to be cheaper for them. And you might have some extra logic, extra unused gates on your current ICs in your project that might help also. That might be, they'll say, well, we want to implement this equation such that we can use some of our unutilized gates on existing hardware and on a given board. So lots of different concepts. I'm not too far into it, but I thought I would work through one example for you. So these are the 8 circuit forms that we just tweaked with. And so the idea here is how many AND gates, OR gates, and NOR, well, how many devices do I need to do this, including inverters? Okay, so this this equation here, let's look at this. We'll just try to do this structured way. I'm gonna need, what am I gonna need? I'm gonna need two inverters. Okay, so that's an inverter for A, an inverter for C. I can reuse the C value, so I don't need 3 inverters on this thing. I need 3 AND gates, and I need one OR gate. Okay, so that's not, I'm not really including the number of inputs on this, I'm just doing it based on gate count. So for this thing I need six devices. Okay, so let's go down here. I see 1, I see 2 inverters. I see 1, 2, 3. These are going to be NOR gates. And I see 1 giant NOR gate. I don't know what I'm thinking. These are NAND gates. And there's 1 giant over NAND on this thing. So that's 6 devices also. So let's look at this thing. I got A. So these are, if you look at these both require 6 devices. So they look, they're equivalent. So let's look at this. I got A, B, C, D. So I need 4 inverters. I need 1, 2, 3 OR gates. And I need 1 NAND gate. So obviously there's more devices on this one compared to the other ones. There's 8 devices there. So let's look at this one. I see A, a B, a C, and D. So there's 4 inverters. I see 3 NOR gates and 1 OR gate. So once again, there's 8 devices. Okay, wow. Pretty exciting. I can see why I don't like doing this. Okay, so from doing the quick view of this thing, these bottom devices here all take 8 devices. These bottom equations, these all take 6 devices. So you could say, in terms of device count, these top options are better.